In this video, we're going to explore some of the basic graphs, sometimes called the parent graphs, the base graphs, or the toolbox functions, and look at how if you tweak the formulas a little bit, you can get what are called transformations of those, where through a set of rules, we can create new graphs from old graphs without having to plot points. However, I'm going to derive the rules and see why they work the way they do by plotting points. So in the first example, we're going to take the toolbox function absolute value of x, plot some points and see what that looks like, and then see what happens if we add 1 or subtract 3 from the formula. Okay, so let's start with the absolute value of x. So what I would do is make a table of points. And I usually like to include some positive and negative numbers, so let's do -2 to 2. That works for a lot of the toolbox functions. Now, absolute value by definition is the distance from 0. So the absolute value of -2 is +2. The absolute value of -1 is +1. So for a negative number, you just knock off the negative sign. The absolute value is 0, and then for any positive number, the absolute value is the number itself. So it's pretty easy to generate a table of points for absolute value. Let me set up an axis here. Okay, so it's a lot easier if you have graph paper under it, but imagine here that I have equally spaced tick marks, and we plot the points. Let's change color. So we've got 0, 0, 1, 1, 2, 2. On the positive side, you actually get the line y equals x, but on the negative side, you also get positive values. You get -1, 1, -2, 2, and so forth. So absolute value of x makes a V shape on the graph. Now what if we wanted to do, say, absolute value of x plus 1? Well, really all you're doing is adding 1 to the y values. I could add a column here, and if I were to evaluate these points from -2 to 2, I would first do the absolute value and get the numbers we had for the previous function, and then add 1. So instead of 2, 1, 0, 1, 2, I would have 3, 2, 1, 2, 3. I'm just taking the y values from the absolute value of x and adding 1 to each of those. This just makes my graph go up 1 in the y direction if I plot those points. And so we call that a vertical shift or a vertical transformation up 1. And then if I were to do absolute value of x minus 3, let's see, let's make it green. So h of x is the absolute value of x minus 3. If I were to do a table, it would be the original values, 2, 1, 0, 1, 2, minus 3. Each y value would go down 3. I'm just going to use the graph to do that. I'm going to take each of the red points and move them down 3 spaces. And we get the graph absolute value of x minus 3. So the result that we have summarized here is if you have any function f of x and you know what its graph looks like, and if c is any positive constant, if you add c, the graph is going to look the same as it did before but shifted up by c units. And if you subtract c, it'll look the same shifted down c units. So those are the vertical shifts. Next, we're going to explore what are called horizontal shifts. Now, vertical shifts, we say, are outside changes to the graph. If you take, for instance, x squared and you did x squared plus 1 on the outside, that would shift it up 1. Horizontal shifts come from manipulating x on the inside. If I replace x inside the square with x plus 2, or inside with x minus 1, that's going to wind up being a horizontal shift. Now, what happens with horizontal shifts, and this is just the way I memorize the rule, we'll see it by plotting some points here, but horizontal shifts kind of work in the opposite direction of what you might think, and that's because we're manipulating the inputs, the x values, instead of the y values. For instance, here, to get my new function, I'm adding 2 to the x's, or I'm subtracting 1 from the x's in the formula. And we kind of have to counter that in our table to create the same y values, and we'll see it shift in the opposite direction. Okay, so, and in the process, we'll learn what x squared looks like. If we don't already know, we get a graph that's called a parabola, but we can do that by plotting points. Again, I'm going to use -2 to 2 to make sure I have some negative and positive values. So -2 squared is 4, -1 squared is 1, 0 squared is 0, and this is what we call an even function. For the negatives and the positives, I get the same y values. 1 squared is 1, 2 squared is 4. So -2 and 2 both give me 4, -1 and 1 both give me 1 when I square them. So when we plot that, we get a U-shaped graph. Has a lot of similarity to absolute value, but because everything's positive, but instead of a V, you get more of a U shape or a parabola. So there's y equals x squared. Now, the rule is, I'm just going to go ahead and graph it by the rule first, and then I'll try to give an explanation with the table. The rule is when you manipulate x on the inside, it's going to move the graph left or right, and it goes in the opposite direction. A plus will actually move it to the left toward the negative numbers. So if I take my original points, I'm just going to move those 3, and I move everything to the left 2 spaces. This would give me x plus 2 squared, or y equals x plus 2 squared. Why is that? Well, one way that I can see that is if I were to make a new table for this function, I could keep the same y values if I were to counteract the x plus 2 with subtracting 2 from the x's. So if I look over here and take these x's and subtract 2, I have -4, -3, -2, -1, and 0. When you plug those in, you add 2 to the x's, you get the same x's you had in the original table. For instance, if I do -2 plus 2 squared, I get 0 squared, which is 0. Or if I do, let's say -4 plus 2 squared, I get -2 squared, which is 4. Okay. So because we're adding 2 in the formula, if we subtract 2 from our x's, we'll have the same y values as the original graph, and you get the transformation in that direction. If I were to make a table for the blue one here for h of x, if I were to add 1 to my x's and then subtract 1 in the formula, I get the same y values as the original graph. So I would have to add 1 in the x direction to keep those y values, and we'd have the shift to the right. Okay, so those are the horizontal shifts. If you take a formula f of x and you know what the graph of that function looks like, and in function notation, if you replace x with x plus c on the inside, you get a shift to the left, assuming c is positive, and if you subtract c, you get a shift to the right. So those are what we call the shifts. The shape of the graph stays exactly the same, but you either move them up or down or left or right. And just remember, vertical goes with the direction of the sign, but horizontal goes in the opposite direction.